Hi, everybody. This is Dr. Dadu presenting some high school mathematical identities you may have missed. Happy listening. In this video, some high school irregular identities are discussed. They are very useful to researchers in number theory, distribution theory, and allied areas. The requirement is that you still recall some of the things you did in your high school. The synopsis will be fundamental theorem on polynomials, the Tartaglia's method, extension, and identities. Any textbook on pure mathematics at advanced level will do as your reference material. Now, if you have a polynomial of the type this, the highest degree is n, the highest degree to which x is raised is n, it can be written in this form. There you have a coefficient and you have the linear multiplication of linear equations, n linear equations. Now, that's to be a general polynomial of degree n. What if you have a cubic equation? Cubic equations are polynomials whose highest degree are 3. The highest degree to which x is raised is 3. Now, whenever a polynomial has a complex root, its complex conjugate is also a root to that polynomial. Now, in cubic equation, since it has 3 roots, if one of them is complex, it means its complex conjugate is also a root, making 2. And it means it has a non-complex root, a real root. That goes for all polynomials. And that's why we say a polynomial will have at least a real root. Cubic, in every case, an equation of the form this can be converted to this by substitution this. This transformation will enable you to usurp the quadratic coefficient. See, the quadratic coefficient is gotten missing here through this transformation. Now, I haven't gone that far. If you are able to usurp the quadratic coefficient and the equation as reduced here, you can now use the Tartaglia method as long as your A is positive. So have your root to be this. However, it looks clumsy, but it's not as tough as it looks. It's just that sometimes even the Tartaglia real root results in complex root because sometimes you have square root of a negative value resulting from here. I mean cube root of a negative value resulting from here. And cube root of I raised to power 3 is equal to minus I. So it will be complex. This part will be imaginary, this part will be real. All right. Whenever that happens, there are some things that you can now do, and that's where the extension comes in. All right. Examples. Question, find the zeros of this. We are putting this transformation, x is equals to y minus 1. When we do that, and we do it very well, we'll see that this results. But this time around, the quadratic coefficient is not usurped. Rather, it's the constant coefficient that is usurped. And that help matters a lot because it enables you to factorize what is given completely. Get its zeros. Return its zeros to this expression, to this linear relationship, your transformation, and it will give you the zeros for x to be this. That's really cool, isn't it? So the transformation can be technically chosen such that the constant coefficient will be usurped, which is the case here. If I had followed the normal transformation, it would have been y plus 1 here. And tell you, but that will not usurp the constant coefficient. So you've got to study it. Sometimes this does the work better. Now, here is another one. Find the root of the equation this, correct to 2 decimal places. Now, this is of the type for which you can use the Tartaglia. Why? Because the coefficient of x is positive, it's greater than 0. So if you use the Tartaglia, you will see that this part will result in complex, just like I explained earlier. So it has to be jettisoned. The real part is the one you pay attention to, and it gives you this. When it now gives you this, you are not done yet, because if you supply this to this equation, the value it will give will be 5.618 dot dot dot. That value is still very far from 0. It is not 0. So you start iterations from here. Start reducing the values little by little, little by little. At least you have a good starting point. By the time you come to 1.29, you have a value that is close to 0 enough. Why did I say close to 0 enough? It's less than 0.05. So, and if you try to reduce it further, you get a value that will be larger than this. You can do that at your leisure anyway. So, giving you that the fact that the 0 is, an acceptable 0 is at x is equal to 1.29. All right. Identities. Now put alpha to be ln A, beta to be ln B, gamma to be ln C, and show that this is equal to 1. Now, solution. If alpha is equal to ln A, then e raised to power alpha is equal to A. Same thing for beta and gamma. Now come back to this expression, the left-hand side, the one that looks so complex and complicated out of the two sides anyway. Then do this, put this transformation there. And this will result, which results into this. And the cut to give you 1. See, that's pretty cool. Identity 2. These are very, very numerous. Identities that has to do with trig ratios. They're very numerous in further maths, and mathematics at advanced level, those who did A levels. You see that you meet this a lot in the questions those days. Now, if you have this to bargain with, say prove that this is equal to this. Solution, just recall that the expansion of the sign ratio is this, while the expansion of the cost ratio is this. All right. Let's look at the left-hand side. It seems that is more complicated than the other one. Now, this we will rewrite as this. Once we rewrite it as this, we will now carry out the expansion. It will fetch us this. After it fetches this, you see that the middle term here is already looking like this, except, of course, for the difference of 2 here. There's 2 here, there's no 2 here. So we said, okay, since this is already looking like this, we keep it aside, combine the first and the third term. First and the third term is written first here, leaving that one that is looking like the right-hand side already. Then we'll now further look at this 2. It's what we're doing here. Again, we carry out the sign expansion on this, and it fetches this. Okay, the cos half theta that is there, cos half theta, then minus that. Now, after getting here, I will carry out the expansion, bring in cos half theta. You are going to have cos squared half theta resulting from there. Now, if you now use the identity that cos squared theta plus sin theta equals 1, then cos squared theta here will be 1 minus sin squared theta. If you introduce that, you have here. If you carry out the expansion here, you see that this part and this part will eliminate each other. This one and this one will go, leaving you with this. Okay, if you now rewrite this, bring in the negative side, negative part to this side, and the positive part to be in the front, and factor out sin theta, these results. Now, let's look at what is in the bracket here. You see that it's more or less an expansion of the cos ratio. The content of this bracket is an expansion of the cos ratio. And that gives you this. Again, this is looking like that. It means this and this actually combines to give 2 of them. So consequently, this is equal to this. Now, the other 2 identities I've discussed, you may have met. They are regular identities that you meet, most especially for those who study further maths or A-level maths those days. How about this one? In your study of factorial, you may not have met this. In factorial, this is equal to this. You meet this if you are reading papers or books, writings involving number theory or distribution theory. Very often that is the case. Now recall that this is equal to this. That's combination. These are combination values anyway. Hence, the left-hand side, which is this, is equal to this if we liter it using this expression. Now, when you get to this part, you see that this simplifies, they simplify to give you this. And after getting here, you see some things cut, like this cutting that, this cutting this. This will have something that cuts it, this cutting that. If you let those things cut, what remains is this, which is the right-hand side. See, you can try this at your leisure. Do it very well because it may not be as easy as just illustrated. That the infinite product, yes, this is much more irregular than the ones we've been seeing. This is equal to this and in turn equal to that. Proof. Recall that here, the numerator here is actually this. You remember sum and difference? This is sum times difference is equal to the difference. Okay, or squares. All right. If you now make this the subject, it will be this divided by this, which explains how this becomes this. How about here? Good. Since we've seen that this is equal to this, we now liter here. The product symbol is telling you that you take product as you iterate n. It means the numerators are having even powers, 2, 4, 6, 8, like that. Whereas the denominator are having natural powers, 1, 2, 3, 4, 5, 7, like that. So if you now let them to cut, this will cut this will cut that of 4. It continues, this will cut this. At the end of the day, you have this, which is equal to this. This is the farthest I intend to go on this issue. Watch out for my next video. Please like, share, and subscribe. Thanks for listening. Bye for now. See you next time. Thank you.